In applications of physics and engineering, you're often working with slanted planes or curved surfaces. And one of the main mathematical tools that you can use to analyze these forces is called projection of vectors. You're basically taking a vector that's slanted and pushing it straight down onto something like taking a shadow. You'll see in just a minute. So let's say that we have an inclined plane and we've got an object on that inclined plane. Then there's a gravitational force that's pulling that object straight down. But what we really want to do is take that force and break it up into two pieces. One piece that's moving parallel to the plane. So that piece of the force is pushing the object to just slide right down the plane. And then another piece of that force that's going perpendicular to the plane. In terms of vectors, instead of saying perpendicular, we'll say it's normal to the plane. So that piece that's normal to the plane will be pinning the object right down onto that slanted surface. It looks a little complicated when you've got it set up like this with this inclined plane, the object, the gravitational force broken up into a couple of different pieces. Let's rewrite the situation just to make it easier on our eyes. So whatever is this, whatever direction the plane is going in, I'm going to rotate it so that that plane looks horizontal. And all I need is a vector that describes that direction, and I'm going to lay that vector flat in this picture. And then the force I'm going to have slanted up, and what I want to do is find the piece of the force that's parallel to the plane, so the piece that's going horizontal. So now you can see why it's called projection, I think. You're taking that vector, you're pushing it straight down onto some direction that you already know about. So let's call this vector, let's call the component of this force P that's moving in the horizontal direction. And then you've got a normal piece as well, let's call that N. We'll solve for P, and then to get N, you can just use the fact that the force F is equal to P plus N. So we've got this natural right triangle that we can use. It's going to be easy to solve this now. Say the angle between the force and the horizontal, or the whatever the direction vector is that you're working with, say that angle is theta. Then we're basically just looking at the base of a triangle here. So we want to get the length of that base, and if I just call the base x, then I know that cosine theta is equal to x divided by the length of f, the length of that force vector. So to get x, just multiply both sides by f, and it's equal to f times cosine theta. That's the length of that projected vector, that p vector. So to get the actual vector p, take that direction vector that you started with v and scale it down so that it just has length 1. So take the unit vector in that direction. It's easy to do this. You can just take the vector v divided by the length of v. And then once you've got it scaled down to a length of 1, then you can multiply it by the length that we just found, f times cosine theta. So the vector p is equal to f cosine theta times the unit vector in that direction. And then if I want n, then I'll just take the original force F and I'll subtract off that P. These projections are not just useful for slanted planes like this. I mentioned curved surfaces earlier. So you may have contexts, for example, fluid flow or electricity and magnetism or heat transfer. Those are all situations that are pretty interesting that you might be studying at some point. In those situations, you've always got this field of vectors, which just means you've got arrows basically at every point. They could be describing fluid flow. So I think you're probably pretty familiar with that, for example, with wind or ocean currents. But you could also do this for electricity and magnetism. For example, a magnetic field. You've got a force at every point in that magnetic field. And then if you want to study, analyze, or solve problems related to a curved surface in the presence of that field, For example, you might want to know how much stuff is moving through that surface. That's called flux. Then what you'll need to be able to do is take that curved surface and look at any given point on the surface and find the vector that represents the fluid flow or the force field at that point. And you want to break down that force or that vector into a piece that's going perpendicular or normal to the surface and a piece that's going parallel to the surface at that point. Because the piece or the component that's going perpendicular is the only piece that's adding something, that's contributing something to the amount that's moving out of the surface. So you'll be able to handle that with an integral. Even though you're looking at individual points, an integral will allow you to follow the smooth surface around. So that's another really nice application that you'll get into eventually of these projected vectors.